All right, we're back yet again, and it's game 2005 in the fall 2017 semester, and it's week 10, part 3 of our broadcast, Energy of a System tutorial, again, part 2. We briefly touched upon this example, really briefly, but the equation is pretty simple to handle. And if you get a question like this, really, it's just taking the example. Now, this is the difficult thing to understand. Why, 30 degrees? Well, because if you notice, if it was straight, then this would equate to 1, right? Here, we're getting a ratio of this 150. And when we multiply it by root 3 over 2, you get less than 150 newtons or 150 joules. You get less than that. So we're taking force, we're applying it over distance, and then we're getting some ratio of the force that we're applying. If, again, just like you think about it when it comes to component forces, if we were to increase this to 90 degrees, perpendicular to the force, like we said, then there would be no work, because when you have cos of 90, it'd be 0, and something times 0 is always 0, so there'd be no work. But if you had some kind of angle closer to the surface, then you'd have a more efficient pull. So what does this mean? It means if I was to pull something, no paper either? Huh? Is there no paper either? There you go. That's why I can't print. If you have a force that is parallel to the surface, and I'm pulling parallel as close to parallel to the surface as possible, so an angle of 0, then it would be equal to 1, which means I would have a better, kind of pull than if I pulled it from an angle. So what does that mean? If I'm pulling something, I definitely want to kind of squat down to pull it, as opposed to stand up if it's on the ground, because it's going to be more difficult to pull something like that. Makes sense, right? You lose energy in the vertical direction. Okay. So that's this example. There's not that many today. Okay. Here's example number 2. All right. So this is another type. So similar to the first example, in this particular case, I'm just going to bring it a little closer so you can see the question text. So you have this, what looks like a bull, right? Calculate the work the bull will perform to push for 2 meters. It's not really written well. A 10-kilogram box sitting on the ground. Okay. If the coefficient of friction between the box and the ground is 0.5. So we have a coefficient of friction. Remember how friction works? We take the coefficient of friction, multiply it by the normal force. So that'd be, in this particular case, 10 kilograms times gravity. Let's assume gravity is 10 in this particular case, not 9.8. That means that's 100. So some kind of 100 is the normal force, multiplied by 0.5 to get the total force of friction, which is 50. Let's say around 50 newtons of force that resists us. So there's 50 newtons of force going this way. You can see all the forces that have been drawn in this diagram. All right, and okay, assume the box is being pulled at a constant velocity. Now notice that this diagram does not show an angle. There's no angle here, right? If it was being pulled at an angle, then we would have that information. So in this particular case, like it says here, the force at which the bull will push the box will be equivalent to, in this particular case, the force of friction, right? Because now they use 9.8, not 10. But if you notice, it'd be like 10 times 10 is 100 times 0.5 is 50. Now you're getting 49.05 because 9.8. And why don't we use cos theta in this case? Because there's no angle, right? No angle means it's actually, I'm pulling at the same or parallel to the ground. That's what this bull is doing. And so it's getting the maximum, kind of efficiency for the pull that it's doing. So the total work that's being done is 49 joules, actually, because it's work over a distance, right? In this particular case, right? Actually, that's the total force that we're using. Now it's asking for calculate the work the bull is pushing. So that's the total amount, right? So 10 kilograms. That's the force of friction. That's what's resisting. That's the total force that I'm applying. This is the force. And then I'm just going straight, right? Now, what's the distance that I'm traveling, right? Because that with no work, work is all about distance. So it says calculate the work per pull being pushed for 2 meters. Okay, so now I haven't calculated that yet. So I take the total force, right? I have the force, and it's force over distance. So I take that 49.05 newtons and multiply it by 2 meters, right? and I get Newton meters, which is joules. And that's the total work that I get. And if you look at that, that's what I'm going to get. I'm going to get 49.05 newtons times 2 meters times 1, because cos of theta, or cos of 0 is 1. We get 98.1 joules. Pretty straightforward stuff. Okay. So that's the first one. That is the whole work thing. How do I do, work? Work is, whenever you think about it, force over distance. Force over distance. Pretty straightforward. All right, here's the next one. Calculate the amount of work done by pulling a 1,000-kilogram brick of gold. I like that one. I want a 1,000-kilogram brick of gold. How about that? Right? That'd be awesome. 1,000 kilograms? Come on. That's huge. On the ground at an angle of 10 degrees if the coefficient of friction is 0.25. All right? Assume the box is being pulled at a constant velocity. Okay, here we have a different problem, right? Slightly different. So we're trying to figure out, calculate the amount of work. So again, it's W that we're trying to figure out, right? So again, here's the free body diagram. We have our friction. Now remember, even though it looks like a free body diagram, we're talking about work of energy of a system. So really, even though it looks like the same as what we do, we talk about the direction of forces, but it's not really a particle anymore. It's a system. So the system that I'm moving is gold, this gold brick, right? And I'm applying a force to it, okay? So I'm pulling the force. You can see that at this angle of 10 degrees right here. So this is the angle that I'm pulling at. So I'm not as efficient as pulling it straight up, which means I'm going to get something less than, what I'm pulling it at. Now I know that here's my normal force, and here's my gravity. So I have what this thing weighs, 1,000 kilograms. Is that what it is? It's crazy, right? It's huge. So 1,000-kilogram brick of gold, right? That means that I take 1,000 times 9.8, right? 9,800 newtons of force is the normal force, right? Now my coefficient of friction, they've given us that as well, is 0.25. So 9,800 times 0.25. So if I was to figure that out, if I say calculator. So 9,800 times 0.25 is equal to 2,450, a unit of 2,450 newtons of force, a frictional force, right? That's the average frictional force that I've got. Okay, so that's what's stopping me. That's what's resisting me. So that's what's going the other way. So I'm pulling this way, right? And I've got frictional forces this way. Okay, so then I know what the force of friction is. I would write that down. Force S for friction is equal to 2,450 newtons, right? Okay, now it says, assume the box is being pulled at a constant velocity. Okay, so I'm moving it. I'm moving this 1,000-kilogram brick of gold for 3 kilometers. 3 kilometers. That's 3,000 meters, right? So now this thing, I'm applying forces to move it at 3,000 meters, right? So I've got, again, now how do I look at this again, right? If I think about what I'm doing, I've been given the mass of the object, right? And work is force over distance, right? Okay, I've been given the mass of the object. I've got the distance of the object. I've got the resistant forces of the object, right? Resistant forces, and I've got the angle, right? So I've got cos of or I've got the angle. I can figure out what that is, right? So what they've done here is exactly that, right? They've kind of put the force of the pull is mass times gravity, right? So this is the coefficient of friction times gravity, right? Over cos theta plus the coefficient times sine theta. Now, how did they get this one? This is the force of the pull. And this is where, you kind of get lost in this stuff, right? But really what they're doing is they're getting a ratio of 0.25 times, which we call 1,000 kilograms times 9.8, and that gives you this first force of the pull. Now, why is this over cos theta plus the coefficient of friction times sine theta? That's the question that you have to think about, right? So it's almost like you've got this one part over the other part to get it's a ratio of forces, right? Why is that? Because you've got your pulling force, right? And then you get your resistance forces, right? So if you didn't have your resistance forces at all, right, then it would be just cos theta times, times the force that's being applied. But we don't know what the force is being applied, right? Remember, it's we want to kind of work it out. And I'll work it out on the board for you. And then maybe I can't show you because I don't have, my iPad's not working. But let's see if I can talk about this for a second. Maybe I type it out for you guys as well. Maybe I'll do that, so I can show other people too. Sorry, it's just trying to figure out how to broadcast. Some people are asking, so I try and do. So if I'll bring up fireworks for a second. Might be the better way to do it. Okay, so in fireworks, let's write some of this stuff out so we can understand it, because I think some of the problem when we break down an issue like this is we don't know how to express it. Let's go with 1024 by 768 for the canvas there. Okay, good. So what we want to talk about here is this idea of all of our knowns. So we know our mass. So the mass of the gold brick is 1,000 kilograms, or sorry, 3,000 kilograms. I'll make this bigger in a second. Mass is equal to 3,000 kilograms. Is that bigger? So then it'll stay big. I'll hopefully remember all my changes. Holy crap. Let's make that 40. Yeah, mass is 3,000 kilograms. All right, cool. And we also know that, is it 1,000? No, 1,000 kilograms. Sorry, it was 3,000 meters. We know the distance we're going, it's 3 kilometers. So that's the total distance. That's the displacement, right? So let's do that too. These are all the knowns. There's a lot of stuff going on. Right, so we know the total displacement. So we can call it, the R value, the change in R is 3,000 meters. We always convert kilometers to meters because we want to keep it in the same units, right? So that's the R value, right? And we know that work is force times times R, right? Force times a change in R, right? And then cos theta. And we know the angle. So the angle, we'll say the angle is 10 degrees, if I'm not wrong. So angle, I don't have a theta, I don't think. Yeah, I'm not going to get a theta right now. So this is going to be angle. Angle is equal to 10 degrees. So 10 degrees, you know all these things. Right? And we also know that the coefficient of friction, which is mu, is 0.25. So, and that's probably the coefficient of kinetic friction, my guess. But it doesn't really tell us. So we'll say friction. So force of friction. Force of friction. Let's call it friction. Right, is, or coefficient of friction, FC, is going to be 0.5 or 0.25. Here we go. All right, so we know these things, right? That's how you start off. And then what we want to try and do is figure out, what the total force of friction is. So that's if you look at the diagram, that's this part here, this F friction, right? So F friction is that, right? So again, if I was going to figure it out, we know that to figure out friction, we want to take the coefficient of friction, right? So total friction is equal to the coefficient of friction multiplied by the normal force, okay? The normal force, that's what it is. And so we don't know the normal force, but we can figure that out. We can say that the normal force, Fn, right, is equal to the mass times gravity, really, at the end of it, because, as whatever, right now we're sitting on top of a surface, and that's what it is. So we have our mass, and we know what gravity is, 9.8. So we can figure out that the normal force, right, which is equal to 1,000, right? Oops. Times 9.8, which it works out to be 9.8, Tom, not 9.3. I know it's just all day today, which is 9,800 newtons. Now again, there's a beauty in not calculating everything at once, but we know these things, right? So force normal is equal to this. So then we want to find the force of friction, which is up here. We know that we can figure this out. Let's put this over here because we know that force normal is equal to this. The force of friction then would be equal to the coefficient of friction, so 0.25, right? Multiplied by the normal force, which is 9,800 newtons, which equates to, I had before, 2,450. So 2,450 newtons. That's the normal force. The force of friction. And it's represented by S, force of friction. All right, so force of friction. So these are the things we know. Force normal, force of friction. Now we need the force of friction. And we also know the equation for work, right? Equation for work, if we didn't have any friction at all, right, is equal to work is equal to the force, applied force, right, times R, right? We'll make it we'll separate it, times R times cos of the angle, right? In this particular case, our angle is 10 degrees, so we'll put that in there. I'll just write angle there so you can see that, cos of the angle. So that's what that is, right? And then we take this, and I apologize for my poor program here, but it is what it is. I mean, I could probably do it other ways. But if we sub in all the values, then we know that we don't know the force. We do know what R is, which is 3,000 meters. And we do know what cos of 10 degrees is. We can figure that out. So let's find that value. So we'll say 10 cos. So it's something like 0.985. Let's round up. Shouldn't do that, but hey, the hell. 0.985. That's our total. And we don't know what force is. We don't know what work is. Okay. So this is what we know. So, and we want to kind of get this idea of this is the force that we're being applied, but we also have this other problem. We have this force, the force of static friction, which is 2,450, right? Multiplied by some value of this angle times this the mass, all right, or sorry, the distance, right? And if we kind of break it down into one value for a second, 3,000, we get this number 295442, which is kind of equal to F times 295442, right? Okay, are we good so far? Right? So those are the numbers. 295442 is too bad. 295442. It's the dot that's missing. Yeah, come on, Tom. Today my electronics is just not working. Maybe it's my brain. That's what it is. My brain's not working today. All right, makes sense? So we got this times force, and then we have this. That's what resists us, right? So if we take this, if you think about logically you'd say, well, we got some value, some scalar quantity times the force is equal to total work, right? Minus 2,450 newtons, because we have resistance. Some kind of forces, right? If we go back to the diagram here, you have some kind of frictional forces resisting the pull. This is the force pulling, right? And that's how we figure out work. Now we don't know what this force pulling is. It says calculate the work, but they've done something. They've gone around and done this. They said, well, the force pulling is some ratio of the force of friction, right, over cos theta plus mu sine theta. We don't have that ratio at all. But when it looks to see what they're doing, this says they take the full total work, which is the force, the pulling force times the distance, right? Pulling force times the distance times cos theta, and they fill that stuff in. They say here's the pulling force times the distance times cos theta, and then they get some value 7 times 10 to the 6th joules. And would be a big value because we're pulling a large object for a long time, right? But how did they get this pulling force, this force of pulling, right? If you look at it. Because we don't have this. We don't have this pulling force. So what do we know, right? We know that we can figure out some parts of it, right? We know we can figure out some parts of it, that it's moving in a particular direction. We have a direction that we're moving. The force of friction is slowing us down, right? And I have to push against the force of friction, right? Now, it says constant speed. We're not given a speed. So it didn't tell us, hey, we're moving at a constant speed of blah, blah. But we know the force of friction is slowing us down, and we're overcoming that force. If there was no force of friction, how much work would we do? So if it's a frictionless surface, let's think about this for a second, right? If I'm pushing an object over a frictionless surface, how much work am I doing? Is it hard? Like completely 100% frictionless, right? The answer is no. Frictional force is actually what we're pushing against, right? So we know we have our force of friction, so to speak, our pulling force, right? But we're pushing against it, and we know that there's nothing else that's slowing us down, right? We're not pushing beyond more than beyond that, right? So it's not just slowing us down, but that is the actual force that we're pulling at. So we take the force of friction, whatever it is, right? And if we take that, if this is true, we look at it the other way around. And if I got my numbers, right? So here's the force of friction. We don't know what this is, but we know this, right? Here's the force of friction, 2450, right? 2450 times 3,000, or 2450 times this value right here. This is what this F is. You're like, what's the F in this whole equation, right? Here's the other thing. This force of friction is totally, kind of resisting us. Why all this other stuff? Why this sine? And we didn't even talk about sine or cosine or anything. Just sine, right? Or just cosine, I mean. So let's take a look at that. Let's see if that works out. So I have this value, right, multiplied by this value. So if I multiply those two things, 2450. Right, we got some value, some big value, 7.2 times 10 to the whatever, right? To the 6, I think it is. I'm not sure if that's the right answer, but that's something like that what we'd be getting, right? Some points, we just figured it out differently. We just move things around a little bit differently. I would figure it out my way. I wouldn't use this system here, right? At the end of the day, it's right. The reason why we're correct is because, we have to figure out what we're doing. In this particular case, the force of friction is telling us how much force we need to push this thing, right? And we know, once we know that, the force that we're pushing with, right? And we know the distance, and we know the angle, we can figure out the work in joules, right? So the total work in joules, if we sub in, instead of just putting F, if we put in Fn, that's really what it is, force of friction, the normal force, or the force of friction, sorry, it's the Fs, then Fs times this value, which equates to 7.2 times 10 to the 6th. And I can't really draw here, but you get the picture. Times 10 to the 6th. We'll use a little caret for that. How about that? 10 to the 6th, the old school way, right? 10 to the 6th. And how do I know this is true? Because when you look at my calculator, 7.2 times 10, 7.2 times 1, 2, 3, 4, 5, 6, 7.2 times 10 to the 6th. Okay. Now it's not accurate. It's not. It's really, 7,238,336.98 joules, right? But it's close, right? Any questions around that? It's not as confusing as it looks. Believe me. It's just trying to figure out when you look at the problem how to break it down into its component parts. All right, that's this one. Okay, problem number 2, 3. Problem number 4. Okay, this is interesting. When doing a chin-up, an athlete lifts her 55-kilogram body a distance of 0.25 meters in 2 seconds, right? What is the power delivered by the athlete's biceps? Okay, so we know that power is equal to work over time. In this particular case, we got the force of gravity, right, times the displacement. Okay, that's what we're using, the force of gravity times displacement. Now, in this particular case, we're moving up and down, right? And we're just changing our axes. So we're just moving this way, right? So the work is being done across the y-axis in this case, not the x-axis, okay? So that's why there's no cos of cos theta. There's no cos theta here, right? But that's what work is. Work is equal to the displacement times the force. So force of gravity, so how much does she weigh? 55 kilograms, right? Times 9.8 meters per second, times the total displacement, which is 0.25 meters. And that is your work, right, in joules. And then you put that over 2 seconds. Remember, it's power is work over time, right? And you get this 67.375, not W, it should be W. It should be watts. Actually, that's correct, watts. It's the W. You know, it kind of confused me. I thought it was work. Watts, because that's how much power there is. That's how much power her biceps are pulling, because she's, you know, she's doing it over a certain time. So work over time is power. Questions around this one? Pretty simple. All we're doing is applying the formula. So nothing crazy or you know, cryptic there. All right, let's go to the next one, if you guys don't have any questions. Okay, now this one we have to figure out. This one, I kind of gave a little bit of some of these without the answers to figure out. So we have a 90-kilogram bike started at rest from the top of a 500 meter long hill with a 30-degree incline. Now this is a different problem. Okay, so let's see if you can draw this out. So we have another problem here. So file new. So 4, 5, 768. We have an incline. Let's draw the picture, right? So we have this incline here, and let's draw it without drawing it in white. How about that? And we'll draw it with some kind of border, make it thicker. There we are. And we have a bike. Okay, this is the incline. And the incline is 30 degrees. So we'll draw some kind of mark. That says 30. Let's draw 30. How about that? And we'll draw the thing here. So this is the plane. So we'll draw the plane here. There's the plane. And then the, just to draw the situation. And this is 30 degrees, right? Some kind of angle of 30 degrees. We got in there, right? And it says that the 90-kilogram bike starts to rest at the top of the hill. And this is 500 meters, all right? So we know that the distance is 500 meters, okay? And can I modify it so that it looks a little better? Maybe I can. Maybe I can. 500 meters. We know that that's the case. And we know that this bike is at the top, and it is 90 kilograms. So we know that there's a bike. Let's just draw a circle for the bike. We can. Circle, Tom. Oh, yeah, I'm really suffering today. There's the circle. It should be empty inside. And we'll make it so that it has some kind of, make it 2. Not 12, 2. Yeah, cool. And there's a circle, and it's at the top of the, I think it's really a bike. Think about this as like a bike wheel, all right? It's the bike on top of the incline. All right, and assuming an average friction force of 60 newtons. Okay, that's interesting. So we've been given the friction force. Where would the friction force be? Along this path right here, all right? 60 newtons is quite small. That's what this thing is, right? Find the speed of the biker at the bottom of the hill. Okay, so this is interesting. So if we're going to draw a free body diagram, if this is the biker, all right, and we've got a couple of things here. We can draw in, make that 3. And we'll draw in the bottom of the hill. We have our mass times gravity. We know that for sure, right? We have a normal force, but the normal force is perpendicular. We have the normal force. And we know that the normal force is perpendicular to the incline, right? That's where we want to put it. We want to kind of put the normal force like this. How about them apples? Huh? There we go. Okay, so we got that. And this is the normal force, and we'll just put that, we'll mark that in place as well. our diagram. So force normal. Okay, does that make sense? We're trying to figure out what it is. Now, what we're being asked to do is to find the speed of the biker at the bottom of the hill. So we're here, right? And we want to really kind of figure out if this is what's going to happen down here, right? So here's what we want at the top of the hill. Here's a bike, right? We're just representing it with a circle. Actually, it doesn't matter. It's a system, right? Who cares if it's a bike? It could be a square, for all you care, right? And we also know that the average friction force is 60 newtons, which means that if we take this and we put it the other way around, we should draw, you know, if I can do it properly. There we go. This got this force going this way, and it is 50 newtons. 50 newtons. We know that is the force of friction. So we'll say the average force of friction, right, is 50 newtons, right? Going that way. Okay, so now it's asking you how fast is it going by the time it gets to the bottom. How do we figure this one out? Anyone have any idea what approach they would take? There's many ways you can do this problem. Okay. Okay, and what are we looking for? We're looking for V. That's a clue, right? V, if I'm looking for V, speed, right? I'm not talking about work anymore, right? Work isn't velocity over speed over distance, right? It's not that. Or speed over distance. Work and power are all around energy, right? And energy, remember there's a work energy kind of mix. One of the things we know is we know that there is a potential energy here, right? What's the potential energy that we have at the top of the hill? How do I figure potential energy out? Well, we know that potential energy, right, in terms of U, right? That's what we call it. The U of gravity, that's all we care about, gravitational potential energy, is really equal to the mass times gravity times the height of the object, right? So we don't know what this height of the object is, do we? We can figure it out with a little bit of trigonometry, right? So we know it's mass times gravity, right, times some kind of height of the object. The higher up it goes, the displacement, if you will, is what the potential energy is, right? Okay, so how do I figure out what height is? Well, we have the hypotenuse, right? And we have the angle, right? And we want to find the opposite. Okay, that's what we have. So we know that this, right, is if you look at SOHCAHTOA, right? SOHCAHTOA is, you know, is the sine of the angle, right? So it's right, because it's opposite, right? Opposite. So it's SOHCAHTOA. It's probably going to be it's probably going to be sine because you've got a rise, right, over the thing, and you've got hypotenuse. So opposite over hypotenuse, right? Opposite over hypotenuse. So you take the opposite over hypotenuse to find to this angle. Well, that's what it is. So if we write that down, let's just write it down. Remember, this is back to trigonometry 101 again. Right. Now, again, there's many ways to figure this out, but you guys can determine which way you like to figure it out. I'm going to use this way because this is the way I know. How about I just actually do this and do this? Yeah. UG is potential energy. Yeah. So I know that that's the case, right? And that's going to tell us a couple things. That's going to tell us the total amount of work that it's going to take, you know, to roll down the hill, right? And then we'll have our speed. Okay, so let's talk about this now. So we know that, you know, if I go to SOHCAHTOA, SOHCAHTOA, right? That old thing, it means a bunch of stuff, right? So if I want to look at, these are all ratios. That's what they are, right? So sine, you know, example, opposite over hypotenuse, right? That's what it is, opposite over hypotenuse, and I get the sine of the angle, right? But we have sine of 30, we know that, right? And we don't know opposite, but we have hypotenuse, right? So opposite over hypotenuse, right, is what we're going to put in there. We don't, so let's put that in there. So let's say something like sine theta is equal to opposite over hypotenuse. And that's back to things. So sine of 30 is equal to opposite, right, which is this thing here. We'll call this the height. That's what the opposite is, height over hypotenuse, which is 500 meters. Right? Those are the things we know. Because, my friends, this is the height. That's what height is. This is the height, and that's the opposite, actually, height, right? So this is it. So now we have to figure out for what h is, right? So we say h is equal to sine 30 over 500 meters. So let's try and figure, let's just rearrange that. So h then is equal to sine 30 sine, right, divided by 500 meters is equal to, whoa, that doesn't make sense. Maybe it does. That actually does not make sense. Sine of 30, hold on a second, 30 sine 0.5 times 500 meters. That's like, yeah, 250 meters. That's more like it. So that's what the height is, 250 meters, right? And to check this, right, you could do your trigonometry, right? You can say a squared plus b squared is equal to c squared, right? You can find all the distances if you really want to. But let's just suppose that the height is 250 meters because that's what we figured out, right? And now we want to find UG, which is our potential energy, right? So if we're going to find that out, now that we have that, let's go here. We can say that UG is equal to mass of the bike, which is, we know is, we say 50 kilograms? How much did we say? 90 kilograms. We didn't write that down. Sorry, that's my mistake. My bad. We also know that mass, we'll put this down here. We figured this out. Oops. We know that mass is equal to 90 kilograms. Okay, know that. So now we can figure this out. We know that mass times gravity times height is this. So we can kind of figure that out. What the hell? Mass, right? Wow, I guess I have another thing there. Did I just, yeah, I did. I don't know how that happened. Well, who cares? We'll just continue with without thinking that I made lots of mistakes today. 90 times gravity, 9.8. Right, times 250. I'll move that down so everyone can see it nicely. Right, that's what this is. That's what UG is. And if you solve for UG, right, actually maybe I'll put it down here so we can have more room. That's a great thing about having one of these digital things here. Move around. And if we solve for UG, that's potential energy, then what is that? That is 90 kilograms times 9.8 meters per second, right, times 250, right, is equal to 220,500. That's the potential energy, 220,500, which makes sense, right? All right, so that's the potential energy we have. And that's here at the top, right? Now we know what's going to happen, right? Potential energy, if you think about what potential energy is, right? It's going to transfer to, with some work, it's going to transfer to kinetic energy at the bottom, right? So, you know, we have something there at the top, and it's equal to the kinetic energy minus the frictional force, right? We have the frictional force. So that's what it's going to equal to, because the energy is conserved, right? Now, we're going to talk about more of this later. I'm going to say, well, we know that, here's the equation we're going to put into play. We know that UG is equal to, right, kinetic energy, right? So let's say kinetic energy, right, minus this frictional force of 50 newtons. Okay, that's what it is. So minus 50 newtons, right? Because it's going to slow us down. That's what it is, right? It's the amount of work. Now, work is the other thing we have to figure out, because it's not just the newtons, right? It's newtons over distance. That's where that 500 meters comes into play, right? We have 500 meters, and we're going against the resistance of 50 newtons for 500 meters, right? So let's go back up and calculate that. Again, I know this is all convoluted. It looks like a convoluted, but really it's straightforward. It's just a matter of trying to figure this out, right? So we know that the work is equal to force times distance, right, times cos of some kind of angle, right? Well, the angle is going straight, so the angle is 0. I don't have to think about cosine anymore. So really, work is equal to force times the total distance traveled, or work is equal to force times, so force is equal to 50 newtons, right? Total times the distance traveled, which is 500 meters, which equates to 25,000 joules. Right? All right. And we know that that equation we got earlier, right? When we put the work together with, this potential energy and kinetic energy, there's some kind of relationship between one and the other, okay? If we look back to potential energy, kinetic energy, which is way up here, I think. And we're not talking about springs yet. That's like coming later. Here it is. So the change in kinetic energy is equal to this, but we also want to find it, how it applies to this. So kinetic energy initial. What's the initial kinetic energy at the top of the hill? 0, right? Because there's nothing moving. So the kinetic energy is going to be transferred to the two, or from the potential energy. So we have this work, right, that we have to do. Notice I put it on the other side, but we can easily transfer it here. So whatever the initial potential energy is, plus the work that's involved, go back to our little equation. I just drew it this way, but it's the same thing at the end of the day, right? But I put it on this side, right? So it's really what they did was they did something like this, right? So we said work as an equation minus, so plus work, which is this thing we just talked about, is equal to kinetic energy, right? This thing here. We already figured out work, right? And now we've already figured out this, right? And now we need to find this, because kinetic energy is what we want to use, right? So let's do that. So we'll say that this is equal to 22,500 or 220,500, right? And then plus our 25,000, right? Equal to this. Let's add that in. Plus 25,000. Right? Is this 245,500? That's what this is. So kinetic energy is equal to 245,500. 245. And if we were asked to find what kinetic energy is, we'd be good. But that's not the answer, right? That's just the kinetic energy. Now, there's a ratio between kinetic energy and velocity. Remember? Kinetic energy is us moving an object times the speed, right? Velocity, right? A mass times the speed. That's what we have. That's what this is. Now, we actually used mass earlier, and we could have probably avoided doing that by having the equations first. So if we look at what kinetic energy is, going back to our little diagram, our little PowerPoint, and if we go to find what kinetic energy is, that's applied forces, that's work, Nah, it's further up. Because maybe just make this a little smaller so we can see where the hell we're doing. That's work done. Here's kinetic energy. So kinetic energy is 1/2 mv squared, right? 1/2 mv squared. So we know if that's the case, we have a ratio of mass times speed. That's what that is, not velocity. V is the speed that we're looking at of the particle, right? Okay. So we know that this is equal to 5, right? Times mass times v squared, right? I just put the 2 so you know what that is. So that's what this is. So then we just take this ratio, 0.5 times 90, and we divide 245,500 by that. Let's do that next. I know it looks like a lot of work, but it's just, I'm just breaking it down really, long. Copy that in there. So we'll say that it's equal to, so we're solving for v squared, right? So we're saying that v squared is equal to 245,500 divided by 45. Divide this by 45 is equal to 5,455. 5455. Make it even. 5455. Okay, fine. I'll put 0.6. There we go. We know that v squared is equal to that, but we're solving for v. We're solving for v. So we take the square root of this. Square root, this one, which is 73.86 meters per second. And let's see, does that make sense? That's what you have to ask yourself. If it's something whack, right? Like, that's pretty fast. All right, so 73.86 meters. 3.86 meters per second. It's v. So we just took the square root of that. Could you have done this differently? Absolutely. How could you have done it differently? Well, we know that velocity or speed is distance over time, right? And we don't know how long it took. We don't know how long it took. But we could figure out from the normal force and this thing here what the actual force of on the x-axis is. We could figure that out because we have this diagram. Remember, we take the angle that we have, this 30 degrees, flip it so that's on the other side, and now we have an inclined plane, like we did with Newtonian physics, right? You know that thing where you have a car on a plane. Remember that whole problem before, right? And once you've got that, you can use force equals to mass times acceleration. So you can do it that way as well, right? F is equal to ma. And you know, in this particular case, that ma is gravity. A is gravity, right? That's what's accelerating you. But we only care about the sine of 30 degrees, that we're multiplying sine of 30 degrees to give us that just on the x-axis, that force on the x-axis. All right, so if I did it that way, just to check our work, the force on the x-axis is sine of 30 degrees, sine of 30 degrees, right? Multiplied by the normal force, right? And the normal force being 90 kilograms times 9.8. So we'll just take this. What the hell? Sine of 30.5. Okay, we'll remember that. Sine of 30 times the normal force, which is 90 kilograms, right? 90 kilograms times 9.8 times 0.5, right? So that's the force of newtons, 441 newtons, right? Hear me? So that's the force that we're getting. That's the force that you're traveling down the hill with. This is another way to do it, right? So 441 newtons minus the 50 newtons that we got from a frictional force perspective, so minus 50, right, is equal to 391 newtons of force by the time we get to the bottom of the hill. 391 newtons of force. right? Okay, we know that force is equal to ma. We know that we can derive acceleration. We can derive velocity from acceleration, right? Whatever the velocity is. We want to find the speed that we're going, right? So we know that what the acceleration is, right? Because we know that force at the bottom is equal to mass times acceleration. This is the force. We know the mass, right? We want to find the acceleration. We take the force divided by the mass. So we got this. 4.34 is the acceleration, right? At the bottom of the hill. 4.34 meters per second squared, right? At the bottom of the hill. But I want to find the distance over time, right? So guess what I want to do? I want to do my I want to go from acceleration to velocity. What do I got to do? I got to multiply. I got to do an integral, right? I'm just telling you, there's different ways of doing the same thing, right? I'm not saying it's right, but look at all the work I have to do the other way around, right? I got to take the integral of this. I got to take this 4.344 and multiply it by time, right? Because right now I have acceleration per second. I want to find meters per second in velocity, right? So we take this and multiply and take the integral of this. So the integral would be, wow, this is like going back the other way around. So this is a constant. So I would just get an x on top of that, right? Which would be t. So multiply that by time. So it'd be this times time, right? But we know that the distance traveled is 500 meters. So we accelerate 4.344 at the bottom. We started here at 0, and when we got to the bottom, we had accelerated 4.344 meters per second. Like that's the acceleration rate that we got to at the bottom of the hill, and we kept accelerating, right? So again, from there you could derive, and I'm not going to do it right now, but you can derive what the initial velocity was. We started at 0 velocity, and we accelerated to, to that point, right? So it's just kinematic equations now, from that perspective, right? So it's like a falling object. You have an object, 1/2 at squared. That's what it is, right? You kind of go back the other way around. So 1/2 at squared is equal to 4.344, and you want to find what t is. You're solving for t. How long does it take, right? And you're going to get some ratio. So this is what this is, 4.344. That is acceleration, right? And you want to find time, right? So you take half of that times 0.5, right? And that's equal to the total time, right? That's t squared. And then you just get the square root. And so 1.47 seconds it takes to go 500 meters. Distance over time, you got velocity, right? So that's how many seconds it takes to go 500 meters, right? Times 500 meters. Oh, sorry, distance over time. 500 divided by 1.47, let's say. 500 divided by, 500 divided by 1.47. And you should have something like really fast. It's not the same. But you see what I'm saying? I would derive it from the other way around. I made a miscalculation. Right? So that, again, there's different ways of doing the same thing, but the kinetic energy, potential energy thing is easier because we know how much energy is there because we found out how high this thing was and it rolled down the hill. Okay? So that's this one. I know it's convoluted, but I wanted to share that with you. All right, next. If no one's asking me any questions, I'm just going to keep rolling through. Next, last question, and then we can go for the day, right? A small car with a mass of 1,000 kilograms traveling at 30 meters per second has its speed reduced to 10 meters per second by a constant braking force over a distance of 75 meters. All right? Find the car's initial kinetic energy. Find the car's final kinetic energy. The net work done, or change in kinetic energy, and find the braking force acting on the car. Okay, so constant braking force is good. That means there's constant forces being applied, right? So how would I do this one? Let's do this one here, all right, to figure this out. So again, I'm going to go to here. I'm going to go to Insert, because now we have room down here to do this. I'm going to do this. Okay, so instead of drawing it there, so we know a couple things. We know the mass of the car, mass M, is equal to 1,000 kilograms. Pretty small car, 3,000 kilograms, right? But that's fine. Okay, so that's the mass of the car. We know the speed. This is the velocity, or the speed that we're traveling. We don't talk velocity in this case. We're just talking about speed. So we know the speed is equal to v, right, which is 30 meters per second. So that's pretty good, right? So the initial, this is the initial kinetic energy, right? How do we find kinetic energy? Well, we know that kinetic energy initial, right, is equal to 1/2 mv squared, right? That's let's say 0.5 m times v. We'll use that caret again, mv squared. So 1/2 mv squared, right? We know that that's the case, right? So if that's the case, then we can figure this out, right? If that's the initial kinetic energy, that's the first part of our question. This is this part, the initial kinetic energy, right? Okay, cool. So we can figure out that 0.5 times the mass of the car, subbing in, times velocity squared, or sorry, speed squared. So it's 30 times 30 is 900, right? And we get some kind of kinetic energy initial, which is something like 0.5 times 1,000, right, times 900 in joules. So 450,000 joules. Now, why is it such a large amount of joules? Because we have a large object that we're moving very fast, right? That's the initial kinetic energy. All right. The speed is reduced to 10 meters per second. So from 30 meters per second, it's reduced to 10 meters per second by a constant braking force. Okay, cool. So we can figure this out again. So we're going to go take this, and we're going to copy it, and we're going to put this over here. And we're going to put 1/2 mv squared again, but it's not, the mass is the same, so 1,000. But the v is not the same. The velocity, sorry, the speed goes down to 10. So 10 times 10 is 100. That's what that is. So it's because 1/2 mv squared, right? Which equates to, and it's not K initial, it's K kinetic energy final. We'll just make it so that you can see that one is different than the other. So kinetic energy final is equal to 0.5 times 1,000, right, times 100, which is 50,000. Joules, right? So we've got 450,000 to 50,000. All right. We did this, right? We used something over a distance of 75 meters. So now we want to find the net work. Yeah. Yeah, so we said that kinetic energy is 0.5 1/2 mv squared, right? So we know that at the beginning, initial, 1,000 kilograms times v, which is 30 meters per second, right? That was the initial. And now we went to 10 because, so actually I should be right. I should put it here so you can see it. So we'll say that this is actually v initial, right? And we'll say that v final is 10. Right? We know those things. I didn't write that down. I didn't record that. Right? So that's what we know. We know that it's going from 30, right, which is over here, to 10, which is over here. Mass is the same. That doesn't change. Somehow we didn't lose a passenger, so the mass is the same, and the car didn't break up like in the atmosphere or something like that. So that's the same. Gas stays probably the same for that length. 75 meters, gas not going to change too much, right? So, and otherwise it's rocket science, eh? Because then we're calculating gas loss over time, and that's like exactly like what's happening with space, right? So we don't want that. We don't want to do that. Okay, so we're just assuming that the gas pretty much stays the same. We can assume those things. So V final, V initial, V final, and then we know that the kinetic energy final is 50,000 joules. Kinetic energy initial is 450,000 joules. So the difference that we have, the difference in kinetic energy, right, is something like 400,000 joules loss, right? Okay, 400,000 joules, right? And what else we calculate in joules? Work, right? We know the work is in joules, and work is amount of force over distance, right? Amount of force over distance, right? So we know that if we calculate the formula, here we go. We know that work is equal to the amount of force, right, applied. So this is braking force. We'll say force braking, right, over distance, right? So we'll say displacement. We'll just call it R, right? Times cos of the angle. Now there's no angle, right? Because it's on a straight plane, right? The force is being applied parallel to the ground, because it's not like there's somehow braking force that's coming from the sky, or you're not going into the ground. You're kind of going this way. You're braking the other way, right? So there's no cos. The cos of the angle is 1, right? So it's really the braking force times the total displacement, right? So we can use this work formula that we kind of came up with, right, to figure this out. We can say that the braking force, then we can rearrange it. The force braking, right, is equal to the work, right, over the distance. That's what it is, right? All we've done is rearrange that algebraically, right? And then, simple algebra. And then we take the total work, which is the difference. The net work is the difference between how much we started off with minus how much we ended up with. That's in joules, right? So we put that in there. So we say, and I'll show you that equation in a second. So that's 400,000. 400,000. Right? And then divided by the distance, which is 75 meters. Right? That's what we've been given. That's the distance that it stopped. It took 75 meters to travel that much. Right? So the network done. And how do we find this network done? How did I find this W network? Well, if you go back to the PowerPoint for a second, up in the top here, so we can find that we got potential energy, we got the equations between work and kinetic energy. Where is that? We have the network down. That's gravitational potential energy. I think it's further up. This is a kinetic energy thing. All right, so yeah, we're close. Here it is. So work, so delta, the difference in work kinetic energy theorem states that work that's being done is the kinetic energy final minus the kinetic energy initial, right? So actually, it's a negative value, right? But it doesn't really matter because it's a scalar, right? So there it is. This is the net work. So kinetic energy is equal kinetic energy final minus kinetic energy initial, right? And if I just take this, just because we're calculating it at the last page, I can do this. And we'll make another, insert another text box here. We know this is true, right? And that's how we got this 400,000 value, right? We took this kinetic energy final, which is this, right? And then minus this, which is, so actually is a negative value here because of the direction of the force, braking force, right? So that is going to equal to, again, 450. Yeah. Love this. 400. See if I can get out of the equation. There we go. Which is equal to 450,000. Actually, no, it's the other way around. It's 50,000 minus 450,000 is equal to 400,000. Right, and that's what this is. I got this because that's what this value is. Again, it looks like a lot, but really I'm just making it longhand so you can see it. Otherwise, I would calculate, a little quicker. Okay, so now we have to figure this out. So what is that? So we're taking a negative value. Let's put a negative sign afterwards for the calculator. So 400,000 divided by 75 is equal to 5,333.3 newtons of force. So negative 5,033.333, non-terminating repeating, right? Newtons of force. And that's this problem. Everyone get that, right? Are you good? You finished? David, you still working on it? You're good? All right. Just bring it up. Bring up your test, please. Bring up your papers. All right, thank you. All right. Okay, so does that make sense? So it's kind of straightforward. The only thing is you have to kind of figure out what they're asking for, right? Now, again, could I have done this differently, right? Think of what I've been given: 1,000 kilograms traveling at 30 meters per second, right? So, right, cool. And now I can always look at it as force is equal to mass times acceleration, right? And acceleration, right? I can determine, you know, this 30 meters per second is the velocity, right? Or speed or whatever. But at the end of the day, you can derive it the other way around, right? So if I have speed, I can derive acceleration, 30t, right? 30 meters per second, right? And I want to take the derivative of 30t, right? So how do I do that? So this is what's the you know, delta time, if you will, right? What from this, I can figure out what acceleration is, right? And when I know what that is, I can figure out the total force. Starting, here's my total force that I'm exerting for the car to go that fast. Force equal to mass times acceleration. If I know what velocity is, I can back up and find out what acceleration. Remember how we did that? We started off a position, right? And we derived velocity, and from there, from velocity, we can derive acceleration, right? So that's how you figure that out. And then again, once you have your force, that's your initial force. We do it for the second one. I do it again. Instead of my acceleration being what it is. Now, and first of all, am I accelerating? I have a constant velocity. What's my acceleration, right? In the initial step, 0, right? But I have a deceleration from 30, right, to 10. That means I'm decelerating 20 meters per second, right, over 75 meters, right? So now I can figure out my deceleration is acceleration, right? And I can find out the force that's involved. So minus 20 meters over 20 meters per second squared over 75 meters. That's the distance, right? And then from there I can find out, it'll almost be the same, right? Actually be the same. This is just figuring out a different way, right? Is it the right thing to do? Hell no, right? This is the right thing to do, right? It's much easier. Okay, but people will try and do it the other way around. I'm not going to stop you, right? If you want to do it use trigonometry or Newton's laws or whatever you want to do, you can totally do it. But it's there's more than one way to do the same thing. So that's really it in a nutshell. We've talked about a few examples, right? And it's all work and kinetic energy today and potential energy. And we started out with this first example, which is this one, which is what work is, right? Which again is force over distance times cos of the angle that you're applying the force, right? Any questions around this? Okay, guys, that's it from me this week. If you have any questions, you can stick around for the assignment, or you can ask questions about your test next week, right? And then David and my other friend over here, can you stick around after because I want to talk about your test, okay? Otherwise, that's it for me.